Well, good morning, everyone. If you could please take your seats, we could get started. I'm João Luiz Azevedo. I work at the Aerospace Technical Center in São José dos Campos, Brazil. And this morning, it is my pleasure to introduce at least the moderator for the IFAR plenary lecture on global cooperation leading to new commercial supersonic opportunity. This lecture will have a few speakers or panelists, if you will, and it will be moderated by Mr. Michel Peters. And what I'll do then is to introduce Michel and then let him introduce all of his speakers, okay? Michel Peters holds a Master of Science degree in Electrical Engineering from the Technical University of Delft with a specialization in avionics engineering. And currently he is the General Director of the NLR. The NLR is the Netherlands Aerospace Center. As you are probably well aware, the NLR is one of the largest technological institutes in the Netherlands and the national knowledge organization in the field of aerospace. Besides his day job at the NLR, Michel also has several positions in various advisory bodies of government and industry in the fields of aeronautics, space, defense, and security. For instance, he is the chairman of the International Forum for Aviation Research, IFAR, that's what the lecture is named after, and he's also a member of the Executive Committee of ICAS. He's a member of the Board of the European Research Establishments in Aeronautics and a member of the European Space Research Establishments. He's also a member of the Advisory Council for Aeronautical Research in Europe, ICAR, or ICAR, I don't know exactly how you guys pronounce it. He's also a member of the German-Dutch wind tunnels and the chairman of the European Transonic Wind Tunnel. He's also a member of the Netherlands Air and Space Agency. So Michel, if you could please join me here at the podium.
Well, thank you very much, ladies and gentlemen. Good morning. Indeed, my name is Michael Peters. Currently here as chairman of IFAR, and started introducing the lecture series on specific supersonic flight. What I will do is first introduce you to IFAR. So let's see if this works. Now IFAR is the International Forum for Aviation Research. Is the world's only aviation research establishment network. And IFAR is established on a voluntary, non-binding basis. IFAR aims to connect research organizations worldwide to enable information exchange and communication on aviation research activities and to develop among its members a shared understanding on challenges faced by global aviation research. Topics include sustainability topics on aviation like emissions, noise, but also security, safety, and efficient operations, and what the title of this lecture series is, preliminary design on, in this case, supersonic flight. It is as you can see, a global organization, and currently we have 26 aviation research organizations from all over the world. As you can see, that's the orange paving part of the world, so there is some room for improvement, but not a lot. And in total, and that's truly impressive, 34,000 high-level skilled engineers working on aviation research. Now the membership in IFAR is open to all national aviation research organizations, including universities active in aviation research, with some caveats, as you can see on the bottom part of this slide. Now the main goal of IFAR is information exchange, do research, as you can see in this graph. On the top left, yes, you see the networking part that is very important, but also, and that's the bottom left in yellow, information exchange and identify priority global research challenges for common actions. Now, like I said in the previous slide, 26 organizations, so we really foster cooperation, and sometimes, of course, it's difficult to define programs and projects where all the 26 members are involved. So bilateral or trilateral or quadrilateral cooperation is of course very much welcome, which you can see on the right-hand side of this slide. Education is also important to young generation, and we could see it, of course, here during the ICAS conference. A lot of young people do an excellent research, and that is really also one of the goals of IFAR to really stimulate the young people. Now, some words about the history of IFAR. Basically, it stems from 2007. Some committee of the IPCC, and I'm just skipping a couple of lines here, but in 2010, then 16 aeronautical research organizations met, and officially IFAR was founded together with the first summit, and in 2011 in Paris, the second one was held. And from that on, so from 2011, each year we have a summit, and in this year that will take place in November at TsAGI in Russia, in Moscow. Now, like I said, cooperation is one of the main drivers what we do. A good example here is what we have done, a couple of partners of IFAR have done on alternative aviation fuels. What you can see here, a proud crew in front of a number of research aircraft of NASA, DLR and NRC doing research on emissions of alternative fuels. You see the DC-8 fueled with alternative fuels, and the Falcon of DLR chasing the aircraft and measuring a lot of stuff. So that's a short introduction of myself, of IFAR, and now focusing on the specific lecture subject, and that's our cooperation on research and cooperation on supersonic flight, supersonic design. And in the order of Sergey Chernyshev of TsAGI will start with a briefing on global supersonic initiatives in Russia. After that, JAXA from Japan will take over and brief us about the activities which are taking place there. After that, NASA at Waggoner will brief us about supersonic research at NASA. After that, Rolf, Henke, Germany, DLR, will brief us about beyond Concorde, supersonic research in Germany and Europe. And last but certainly not least, from France, ONERA, Mr. DLR talks about research actions on noise simulation for sonic boom. And after that I will wrap up, and then we go to the award ceremony together with the President of ICAS, Susan Ying. Thank you very much. Sergey, please.
Good morning, dear ladies and gentlemen. Susan, the chairman of this well-respected around the world Aerospace Council for Aerospace Sciences, founded, I think, more than 60 years ago by Professor von Karman. I'd like to start with very routine situation. I just entered coming here to this Congress. We chose for some reason eastern route, flying from Moscow to São Paulo, and we spent with my colleague Sophia Bluger 20 years in the air. So 4.5 hours Moscow, Doka, and then from there to here 15 hours in the air. It's so boring, in spite, our status allows us to fly business class. Sorry, other TsAGI fellows who flew economic class, but even in business, it's so boring, and your body, with pain, and you don't know what to do, reading everything, your head is like full of bad thoughts, and I thought that I was thinking that yes, it's certainly there is right time to start really serious efforts to develop vehicles that could fly much faster. And that's exactly the session dedicated to supersonic commercial airplanes, where we are. And I'd like to start with, oh, Michel, you forgot to show the last slide. The future of international collaboration. You see the various routes, and I think in the future they will include the routes of supersonic airplanes flying around the world. I mean, very fast. In 3 hours, and you are in any place of the world from your home destination. Right. This is a typical picture that represents market demand. You know, today's dream of every busy person to have to accomplish business mission, you know, to have face-to-face meetings somewhere remote, very remote, and it's big desire, even dream, to return back home at the same day, to start early morning and then return back home the same day. But today's typical approach is different. You know, if we use subsonic aircraft flying around speed of sound a bit lower, 850 kilometers per hour, then even to fly to Europe for the meetings, we spend 3 days. So first day night we leave Moscow, then next day meeting, and typically schedules are so you fly red-eye flight, I think like midnight, or you fly back next morning. So 3 days out of your life, you know. And this is typical route we showed for to reach Vladivostok from Moscow with 7,000 kilometers distance. It's the shortest time you can spend. It's 2 hours, you know, to accomplish your mission. So you start early morning, then fly 7 hours from Moscow to Vladivostok, spend 4 or 5 hours in the meeting place, meet your friends, colleagues, then stay in overnight in a hotel, 10 hours, and then return back against wind, so not 7 but 8 hours. So 2 days. With supersonic flight that can fly twice faster, it's a one-day mission. So early morning you wake up, then airport, workplace, and returning back home at night. A dream. And we showed from Russian perspective several routes that we consider very important, you know, and that we frequent fly, you know, like Astana, Beijing, Khabarovsk, and eastern part, and of course the New World, New York, and US, South America. So it's typical like 7,500, 8,000 kilometers. And again, with supersonic aviation, we can accomplish our business mission during 1 day, and that's really big attraction. Road has changed, and demand from the market already exists. So there are many people who would love to fly faster and pay high price for that, but that's a cost of being efficient and accomplish your mission in short time frame. Looking back, I mean, we should mention experience that we can consider like world experience in the first generation supersonic transport. So Concorde and Tupolev 144, they entered into service almost at the same time. Not so much Tupolev, there were several flights shown here in red map, you know, Moscow, Khabarovsk, Moscow, Almaty, but not so much commercial flights. It was more experimental flights of aviation experts, some measurements and everything, but there was quite extended service of Concorde. Of course, they were much beyond of any reasonable requirements for the civil aviation. I mean, very high noise, unacceptable noise. So in today's metrics, like 9606 dBA. So today's understanding and current target would be something close to 65 dBA. So you see it's huge, and every 3 dB, it's almost twice decrease of energy or increase of energy of sound. So it's huge progress must be done. Overpressure, so which measure shock wave intensity. For previous generation was 120, 140. Today's understanding something like 7-10 times less. So we rely on some US experiments and many people responses. That something like 15 Pascal would be might be considered as candidate for acceptable level. So it's almost 10 times less than characteristics of Concorde and Tupolev. And so noise, of course, beyond of any reasonable limits, they exceeded even noise of chapter 3 ICAO. And our goal today, not only to fit into chapter 14 requirement, to make it 2-3 dB less even in today's acting ICAO chapter 14. Emission decrease, it's 60-75%, or almost twice, depending what we are talking about, CO, CO2, NOx emission. So it's huge progress must be made, must be done. And of course, we can hardly talk today about large size aircraft, because large size, heavy weight, it's the problem of emission, noise, sonic boom become tougher. But smaller size aircraft is kind of first candidate to be introduced on the market. And another important thing I mentioned in the beginning, there is demand from the market. Demand from the people, business people, who fly a lot and who value time as one of the main value of their life. So several projects we showed here from open media, so there might be some incorrect data, but that's what global picture of today. As the last line, I would like to emphasize our United Aircraft Company and Sukhoi having plans to develop such aircraft after demonstration, acceptance level of sonic boom will be validated, demonstration in flight. And very quickly, of course, I'm not trying to show materials that will be presented my colleagues from different part of the world and labs, research labs. But just very quickly, the current projects, very important, demonstrate technology, the technology demonstration that is going on in the US with first flight or rollout, I'm not sure, early 2020 or maybe 2019? 21, okay. So what you will tell Ed? This is very important. So this is something we cannot prove that we developed everything we need just on ground testing, like for regular aircraft, subsonic aircraft. It's a new vehicle, and all technology must be validated in real flight. And particularly important to validate acceptance level of noise and sonic boom for such a type of vehicles. And that's real flight, and many statistical data from population in different parts of the world, and so on and so on. JAXA problem will be covered a bit later in more details, but that's important testing program, flight demonstration that's going from still active from 2011. So very valuable data was received, and again we appreciate very much that Japanese colleagues publish data a lot, and they share on such conferences. So that's also important technology progress shown. Russia, yes, we have, I mentioned already the companies, United Aircraft Company and Sukhoi that started some kind of preliminary design work. Of course, they rely a lot on research establishments, TsAGI and other research institutes, CIAM, Air Propulsion Research Institute, on the concept design that we are doing right now. And our first step would be to develop flight demonstrator also, and have technology demonstration, technology proof in flight, and to get some extra data, some responses from the populations in different parts of Russia. Colder part, Siberia, European part, so on. So by December 2019, we a little bit behind of, let's say, NASA in this case. By December 2019, we'll have completed the design of flight demonstrator. So also, like with the US colleagues, we use and rely on already existing aircraft and taking parts from some high-performance aircraft, fighters, and so on. That's why the demonstrator weight will be not 55 like for expected final design of aircraft, but only 27 tons. And this is the list of key technologies that must be developed. That's not full list. Of course, we can add more and more depending on discipline or experience. But of course, first, the most important, I would say, critical for the supersonic airplane is low sonic boom and low community noise technologies. Fuel efficiency and the low operating cost is something that today are very important for airline companies who will operate this aircraft, and we face with the very contrary requirements: good aerodynamic efficiency, and low sonic boom. They're going against each other. So that's one of the optimization and compromise that must be chosen. Variable cycle and adjustable inlet and nozzle power plant design. That's, of course, there is no existing engine that's ready to be installed on future next generation supersonic transport. And of course, we think that this aircraft will bring some new technology that not used today in existing generation of subsonic aircraft. Let's say like external visualization via artificial vision system. So to install windows, even in the cockpit, it's always a challenge for long-term flight. I mean, 3 hours, heated and everything. So, but for that, of course, the rules, regulations must be edited to allow fly without windows, for example, using just liquid crystal panels or something like this. And material-wise, so new materials, composite structure, composite metal, I think that is agreed, so net structure would be very appropriate to save weight and make weight efficiency, and have weight efficiency for this type of aircraft. Of course, much higher level of artificial intelligence, so high speeds, complicated takeoff and landing operations and regimes that must be supported a lot by artificial intelligence. And of course, introduction of such new vehicle that will fly, the cruise flight will be, altitude of cruise flight will be between 14 and 16 kilometers. Of course, must be, the global air transportation system must be changed and accommodate such type of vehicles. They should go through all trajectories of subsonic aircraft and then go down for landing also. So it's a 4D trajectory, very precise planning of aircraft trajectory, and of course new system, new approach for overall traffic management. I would like to mention some previously accomplished or current international project that supported and supports the current efforts in developing supersonic transport. First of all, under FP6 European Research Program, FRAME program, there was project ISAC. So Bruno remembers, was one of the key player from Dassault Aviation. But you know, we did we researched several shapes, configurations, and we competed inside even our team, completed different rock packages, not only a low sonic boom, but try to see if we have laminar flow, what will be lift to drag, dynamic efficiency, and so on and so on. It was very important and very impressive team, led by Dasovesio at that time. So from 2005 to 2009. Completed. And the current acting project, Rumble, mainly dedicated to regulations and norms for low sonic boom level. Probably you know that there is a ICAO supersonic research roadmap. That map was developed in order to have confidence and proved agreement from the public and from authorities, regulators, that overland supersonic flight is acceptable. So a lot of must be done. You see, I mean, each item is really big scale work and work together of many entities. So for IFAR, the pink for Rumble Alliance, pink color, we developed some complementary value-added roadmap that will provide some extra data helping to reach such very important decision. What is acceptable sonic boom level, what metrics, and so on and so on. So key challenges that must be addressed for the new generation supersonic transport look like this. So international standards for acceptable sonic boom level, of course, for land flight, it's #1. Without that, it's just a waste of efforts and resources. Variable cycle engine with adjustable inlet and nozzle, also something that's very new and should be reliable, must be reliable, very fuel efficient, and not very noisy and low noise. That's something that we should work on, engine companies and all alliance, Aerospace Alliance together. I mentioned optimal trade-off between aerodynamics and of high performance and low sonic boom. That's optimal solution must be received, approved, validated, and bad thing that it's maybe not very optimistic forecast, but statement. But from various perspectives, supersonic airplane must be same level friendly to environment, to people as a subsonic airplane. But physically, you know, we fly so fast and it generates so much disturbances around aircraft that's it's very difficult to fit, to accomplish. Anyway, we need to find the optimal trade-off. And I already mentioned again, operation of such aircraft integrated into the global ATM system, it's also a big challenge. So success in reintroducing commercially viable new generation supersonic transport highly depends on those three most important issues. Successfully solved issues, problems. So joint work and worldwide cooperation of R&D organizations like within IFAR or outside of IFAR, beyond IFAR, design and manufacturing corporations, regulators, and political decision makers are critically important. So it's really joint work. It's very serious challenge, you know, technological challenge, and again, sharing pre-competitive data, we can go faster in reaching success. Flight demonstration of key technologies, including low boom, low noise technologies, variable, I mentioned variable cycle engine with adjustable inlet nozzle. It's some other technologies, again, crucially important. And validation of boom levels on a global scale, because something that is acceptable, let's say, in some part of Russia, may be not acceptable for different part of Russia. And also European, Asian, and different countries, we have all different mentality, culture, and that's a big, big issue that must be resolved, again, in joint work of politicians, regulators, engineers, and so on. So that's the main message I'd like to send, kind of like overall review. And the next one, Michel, you mentioned message from JAXA. As I learned, JAXA is going through some transformation right now, in leadership transformation. So they asked, and we very much appreciate such trust relationship, to make a presentation on behalf of JAXA, me, so they asked me. And I think it's a great honor to share with you the data. Fortunately, the previous, I think, or maybe 4 years ago, I was chair of the session that presented very important work of Japanese colleagues on supersonic transport. So that's why I'm quite familiar, and visited Japan a few times, and we even were involved in especially organized supersonic conference on various issues. So let's do, and I have some text, so it's to be very precise and not look like my personal opinion, but opinion of very well-respected Japanese aerospace agency. So there were several stages for the development of supersonic transport in Japan. So this there is titles of the three of them: next program, S3 program, and S4 program. And a short description is there, and main purpose. So the first efforts just began. First efforts on SST, JAXA began in 1997. And they, of course, have incrementally progressed through several research programs focusing on specific goals. So first one, next program, National Experimental Supersonic Transport Program, launched in 1997, and was focused on drag reduction. While the followed programs S3 and S4, S3 is a silent supersonic technology, as S4 is previous program integration systems. So everything was developed under S3 program was integrated under S4 program, silent supersonic system integration technology program. Collaboration with IFAR member organizations such as NASA, ONERA, DLR, JAXA continued to engage in basic technology research while conducting technology demonstration in 2005, 2011, and 2015. I mentioned already that JAXA has actively provided data from this flight demonstration to ICAS and other colleagues who are involved in supersonic transport development or demonstrator development, and that's really, really high value. Some data that were obtained, so it's some highlights of JAXA's first program, launched in 1997. So it's sonic boom exposure areas, and since it was dedicated to drag reduction, some liminarity in the left corner picture. And to validate this new design concept, JAXA successfully conducted a flight demonstration in Woomera, South Australia in 2005, using unmanned and scaled experimental airplane called Next One, where a laminar in transition flow was achieved over 40% of upper surface. Some dots you can see here. So yellow line or green, light green line is a transition line, laminar turbulent transition line. Then this national laminar flow wing design concept was further extended to high Reynolds number conditions for a larger supersonic transport, already aircraft under development. The results of the flight experiment were presented at ICAS 2010. This is when I chaired this section of presented by JAXA. So DSAT project. So JAXA, after first program, moved to silent supersonic technology research program, or they called it S3. The focus was placed on developing technologies to solve environmental issues such as low sonic boom, low noise at takeoff and landing phase. In 2010, JAXA launched a flight test project called DSAT, drop test for simplified evaluation of non-symmetrically distributed sonic boom to demonstrate its low boom design concept. While non-symmetrically, because it was in real condition with wind, non-homogeneous atmosphere, its temperature distribution, wind density, and so on. And that's very amazing. I mean, for those who was involved or maybe know the details of such type of arrangements, it's really, really complicated program. So the synchronization of all the participated vehicles and tools of measurement like balloons, research aircraft, some other gauges distributed on the ground. Synchronization was very, very precise because you must know that you received pressure distribution with a certain atmosphere condition in order to validate your computer code and the data, and then it's very important for comparison. So that was done, and the scale of the model are very large, so it's about, I think, 5-6, maybe colleagues will correct me, I didn't find in this presentation materials, about 5-6 meters long, fully unmanned, with landing gear that going down, you know, when it's landing, so it's very sophisticated experimental arrangements, and of course, some extra data were received as a contribution to the ICAO, sonic boom acceptance level work. It's in right corner. Some simulated signatures of the sonic boom. So now the third part of ongoing over a decade program called S4. The main objective is to integrate all the technologies received in previous program S3. So a little bit about experimental conditions. The experimental airplane was launched using balloon system at the altitude of 30 kilometers. The experimental airplane was separated from the balloon and accelerating into supersonic speed during its fall. And during this stage, experimental airplane was controlled automatically and glided over the targeted boom measurement system at Mach 139. This is what was received. With a flight path angle of 47.5 degrees. The pressure waveform generated by the boom that propagates vertically toward the ground was measured also. JAXA succeeded in the flight test validating its design concept and improved the concept actually. And the principal results were also presented at the Supersonic technology group meeting. I think it's ICAO working group. So in S4 program, JAXA is engaging in the system integration of technologies developed in previous program I mentioned. Under this program, JAXA has established a technology reference airplane and technology targets, while also achieving improved low boom design concept as well as concepts for reducing noise of airframe and landing gear noise during landing regime of flight. And the current efforts of JAXA is aiming to realize flight demonstration of an experimental vehicle with S4 technologies within the current research midterm program, with both with the continuing program until 2025. So that's a short kind of overview of JAXA's efforts, and you can see that very valuable data has already received and receiving today during implementation of the current research program. So that's I accomplished my mission. I hope that JAXA people will not be upset that I presented everything correctly. So, Michel, it's your turn now.
No, it's not.
To introduce another one.
NASA. NASA.
Okay, NASA. So you want me to introduce
Yes,
Waggoner, our dear friend from NASA headquarters.
So, Madam Chairman and delegates to the ICAS 2018 Congress, it's indeed an honor for me to represent the men and women researchers of NASA Aeronautics here today. And I bring the regrets of Jae-Won Shin, my boss, NASA's representative to IFAR, former chairman. But I guess in about 2 hours, Jae-Won will be advocating NASA's 2020 budget to the White House. So this covers the years 2019 through 2024. So we're really excited about that. I was reflecting Monday morning, the first time I attended ICAS meeting was in 1984 in Toulouse. So the technologies have really changed over that time. At that time I was talking about effect of heavy rain on high lift aerodynamics. But one thing that hasn't changed is the warmth of the delegates and the collegial atmosphere that we find here at each of the congresses. So we've talked a lot about innovations in commercial supersonic flight. I'm not going to spend a lot of additional time on this, but just know that we recognize that there is a market out there, an emerging market, and particularly with the global demand for air travel, and as Sergey talked about, a demand on speed and getting from place to place and just as efficiently as we can. So we feel like that there is a large potential commercial market, probably starting, of course, with business aircraft and then growing to larger commercial aircraft. And we're going to talk a little bit about one of the key barriers and the role that the government plays in developing the data needed to change the regulations that now restrict supersonic flight over land. So one of the things that we've noticed, even with the current restrictions that there are on supersonic flight over land, that there's several commercial companies are are actually developing vehicles that they think will be viable in the marketplace. And in particular in the US, Ariane and Boom, we know that they've talked to the FAA, both of these. Boom Aerospace has actually indicated to the FAA that they'll be applying for a type certificate for their vehicle. But currently, as we've talked about, these restrictions on unacceptable boom over land is viewed as a main barrier to ever achieving this vision. But we think that the technology is in place now to be able to fly over land without an unacceptable boom situation compared, of course, to the Concorde or the SST. And we feel like that the technology is there to develop an aircraft that not only will have low boom, but will be efficient, affordable, and environmentally responsible. So how do we do this? How do we overcome this barrier for overland flight? So new standards are needed. And what's behind any new standards are data, valid data. So proof for the new design requirements, that's going to be the key to replacing any current restrictions. And currently right now there's really not relevant data on aircraft that are size equivalent to a business jet. So we need community data over a large, diverse population, and we need that to inform the regulators that are going to address the standards. So NASA's low boom flight demonstration project is specifically planned to provide those data. So we don't think that the design that we're building is necessarily a design for a business jet, but it is a design that adheres to very exacting requirements from an outer mold line point of view to generate those key data needed to inform the standards community relative to what are acceptable sound levels for commercial supersonic flight over land. So this is a fairly large project for NASA, 3 phases. Almost $500 million, $470 million. We've divided this into 3 phases, and they're really pretty simple. The first phase is a noise generator. That's the vehicle. Detailed design, exacting requirements for that vehicle. We'll do the fabrication, integration, and testing. First flight will be in 2021. And then we'll start on envelope expansion, understanding how that vehicle flies. That vehicle built to these very exacting requirements. Then we'll go into the acoustic validation phase over the next year in 2022. So we'll measure the characteristics of this vehicle, the acoustic characteristics over the flight envelope, and understand what the boom should sound like over the flight envelope. So then that will give us the information needed when we start doing the community response testing. So we have an experimental design that will fly over 6 different campaigns over different communities that have different populations, different environmental conditions, and we'll do that in a way that will be much like what an actual commercial vehicle would do. Many flights per day over the same people for about a month. We'll take these data, we'll analyze these data, and then we will have initial data available for the FAA and ICAO. The first data will be handed off about a year before the Cape 13 meeting. We'll have those data available in 2024, in early 2024. And then in the latter part of 2025, our plan is to have the entire database available and ready for the Cape 14 meeting as it takes place. So we've got a great team with Lockheed Martin building this configuration. This is the X-59. We call it QUEST, standing for Quiet Supersonic Technology. You can see some of the characteristics of the airplane, slightly less than 100 feet long, 30-foot span, designed to fly at Mach 1.4 at about 55,000 feet. So key requirements for this aircraft are an acoustic signal that will be representative of a commercial vehicle. We'll be obtaining the data of sufficient quality to inform the regulatory community, both in the US and internationally, of what public acceptance of these sound levels generated by this vehicle will be. So we're really excited at NASA. We're underway. We planned a comprehensive program to provide these data. 3 phases, as I've said: the aircraft, the envelope expansion, and initial community or acoustic validation of the design requirements, and then the community response testing, 6 different flight campaigns. With the first flight in 21, the first data available for Cape 13 in early 24, and then the full NASA database available for the regulatory community available in late 25, available for Cape 14. So that's a very high-level explanation of what we're doing. We are so thrilled and excited to be doing this back in the X-plane business. So in subsequent years, you'll be hearing much more about this. So what I'd like to do now is turn it over to my colleague Rolf Henke, who will be talking about the work at DLR and other parts of Europe.
I did it. Oh my God, sorry.
So, after Russia, Japan, US, now to old Europe, beyond Concorde, we heard many things already about what has been done in the past and what will happen now. And everything has been said, but not by everybody, so now it's up to me. These 2 aircraft have been shown more than once. These are the only ones, still the only ones on commercial supersonic flight which have been realized, the Concorde and the Tupolev, around 1970. That's civil application. Apart from that, of course, in Europe we had a couple of military applications. Indeed, aerodynamics is almost the same. If you fly supersonic, you have a boom and all this other sort of thing. The Mirage, Tornado, Gripen, Rafale, all these different fighter aircraft. In between, we had a couple of studies from Lockheed, from Boeing, again from Tupolev. And just recently, we find more and more studies on new supersonic commercial aircraft. From Airbus, from JAXA, we have seen it already, and others, and now the size has quite decreased. Concorde was about 192 to 100 passengers. Now we talk about more or less a small aircraft, 8, 10, 20 seats, which from my point of view really makes sense to start with such an aircraft and maybe later on have a bigger one. So that's history. The legacy of Concorde, on the one hand side, is a technical perspective. We have done a lot. We, meaning the community, has done a lot on by Concorde. Flight control systems, the FADEC, the full authority digital engine control, was first in Concorde, and then later it's a usual standard in all aircraft. We had carbon anti-skid brakes, we had a group nose, we have a variable engine intake design. Sergey mentioned this is needed for supersonic aircraft, so first steps have been taken here. In addition, there's a political perspective. So it was a transnational program, in this case between UK and France, paving the way finally up to Airbus, which is also a transnational program. This all started in Europe actually with a Transall, a program between France and Germany, and then military transport aircraft in the 58. But still these sort of programs finally led to a very successful Airbus program as of today. In Germany, we haven't built supersonic aircraft. We have done a lot on aerodynamics. Somewhere in the late 70s, STARB was founded. STARB is an abbreviation for Strömung mit Ablösung, saying flow with separation. It's a community of mainly aerodynamicists, flight physics people, and this group is still active. They meet twice, they have a workshop every year, and every other year a symposium. And it started all with Concorde successor and supersonic flow, separated flow. It's mainly focusing on flight physics, transport aircraft design, hypersonics, aerothermodynamics, high agile configurations, all of this. So they still meet. We do a lot of research still in this area, and this is mainly done by this STARB group. Actually, that was my own work being done somewhere in Cranfield. Murray and I have been there at the same time. Somewhere around 1980, lease had flow over delta wings. We all were really keen on the Concorde successor. So at that time I was able to work by myself, now doing different things. Anyway, I think what is needed, apart from all the aerodynamic work, we need infrastructures. There are a couple of supersonic and even hypersonic wind tunnels throughout Europe, in France, in UK, in Belgium, in Germany. EGW as a European wind tunnel is capable to go up to about Mach 1.4. So we have seen the JAXA aircraft of 1.39, which would just fit. So there are a couple of supersonic facilities which are needed today, mainly in a military application if it comes to supersonic, but they will be needed if it comes to civil applications. In Germany, we focused throughout the years not so much on supersonic aircraft, apart from this flight physics part, but more on space design and space liners. It started with Eugen Sänger in the 1940s, and there was a Sänger program, a pretty big program in Germany around 1990. Hermes was first by CNES, by the French organization, then picked up by ESA. There were again a couple of tests. I first did some tests on Hermes Shield in the BKI tunnel in Brussels. There was a program called New Ways into Space, again on supersonic, hypersonic and fundamental research, founded by the German Research Foundation. And finally at DLR, since 2005 we have getting another space liner, a small space liner. And we heard Sergey that he wants to gain time, and half the time, and this type of aircraft, there's always 1 hour. It's 1 hour from London to New York, it's 1 hour from Frankfurt. For some reasons, it's a law of nature that these aircraft always fly 1 hour. And that's some part of the research which takes place in Germany these days. We already heard about European research programs. There are not the real big ones like Clean Sky, but still a couple of programs starting or more than 20 years ago. These are the last 20 years, 1998 to today. And Rumble has already been addressed by Sergey, and we will hear more about Rumble in the next presentation. In addition, we have several multilateral cooperations apart from the European ones. DLR ONERA have somehow aligned our civil aircraft programs. We have a trilateral agreement, DLR ONERA-JAXA, has already been mentioned, in this case on sonic boom assessment for future supersonic on wood noise standards. So there are still some activities, not that big that you could build an aircraft out of it, but even though to keep the knowledge and to keep the pace in supersonic design. At DLR, our current activities, German Aerospace Center is not so much on aircraft design. We still do some design activities, but it's more to look on the applications, like supersonic routes, assuming that we still have to can fly supersonic only over water, that we have to fly subsonic over land. What would be the best routes, and fly as long as over water as you can in order to optimize the time and minimize the time. What would be the cost? Taking an Arion AS2 aircraft, design it, we redesigned it and taken all this data which are available, and then come to the ESC calculations here behind me, and it would come to a ticket price of a bit more than $2,000 for a flight from London to New York for such an aircraft. So this sort of work is carried out by DLR, more on the system design and on the application of supersonic aircraft, as again, we don't build too many aircraft in Germany. So this is a picture of the Concorde, Concorde times. Coming to summary, so no other commercial supersonic aircraft has been realized for the last decades after Concorde and Tupolev. Infrastructure and technology know-how has been preserved around the world. It's still used in military programs, and it's still available. We have quite some work on space liners like Sänger, Horus and others, but they remain a vision today. The German industry and the research landscape focuses more on the overall system and its utilization. And a more personal outlook, I would think that the new kind of this development pressure, what you need if you want to have a new system and a new aircraft, may come from venture capital companies or new companies, new billionaires like Google, Amazon and others. Either they want to possess it for themselves or they will want to build something for premium passengers. If this doesn't show up, if there's no development pressure on the system, there may be no urgent need to start such a costly supersonic program. It will cost a bigger one around $30 billion or more. And again, Airbus, Boeing and all the other big ones, they earn good money today with a classic aircraft. Why should they invest such amount of money for a new type of aircraft which still has to find its way to the market? So we keep on with the business, we keep on with research.
Provide high quality data to regulation agencies such as ICAO. That's why we are doing this research. The fact that we are still in a pre-competitive stage is a great opportunity for international collaboration on supersonic. So these are some examples of past research. Recent research, what I'm presenting started around 2000. So we are doing most of our activities in collaborations, either internally in France with INRIA or UPMC, for example. We had a collaboration with JAXA that ended in 2016. We have collaborated with Stanford, and more recently participated to the IAAA Sonic Boom Prediction Workshop, the first and the second one actually. So we signed in 2016 a new collaboration with DLR and JAXA focused on Sonic Boom. There are different work packages in this collaboration. First, there is a work package focused on design for low boom. A second one that is focused on en route noise assessment. So we are not only looking at under-track noise, we are also looking at the secondary carpets, how the maneuvers and the trajectory of the aircraft influence the sonic boom. And in a third work package, we also take into account the atmospheric turbulence and its impact on sonic boom. So for example, based on statistical analysis, we evaluate the probability due to local atmospheric turbulence to have a sonic boom that could be multiplied by 2, by 3. What are the chances? And this is an interesting input for regulatory aspects. Another collaboration was signed recently with NASA. So this is basically the continuation of what we have achieved in the IAAA Sonic Boom, the second Sonic Boom Prediction workshop. In that workshop, we focused on the near field Sonic Boom prediction. And in the frame of that collaboration, we focused only on the far field, so how the sonic boom propagates to the ground, and also on the psychoacoustic effects on the population. Another collaboration is occurring within the Rumble project. So this is a Europe-Russia cooperation, including 3 different European partners and 6 partners from Russia. Within this project, we are focusing on different aspects. So first of all, the sonic boom prediction itself. So that's you can see on the left side the classical way to predict sonic boom. So you calculate the acoustic sources through near field CFD. Then you recalculate the Witten function on a cylinder around the aircraft, and you propagate that signal to the ground with a different tool. Yesterday I've seen a very interesting presentation that shows a different way to do it in a full field calculation. This is probably the future. We'll hear more about it. There is also a work package that is focused on human response for psychoacoustic. There is low boom design activities, purely numerical. There is also wind tunnel test that is scheduled in ONERA S2MA wind tunnel. This is not the actual picture of the model because that's taken from the ICAS project, the PATS project, but that's basically the idea. And there are also some flight run measurements, data acquisition from a flight test that will be led by TsAGI. So there are two different campaigns that are scheduled. The first one to really prepare the data acquisition, and the second one that will be a mock-up certification process for what could be a certification process for a civil aircraft. And it will be performed on already existing fighter aircraft. So, as you have probably seen, this is supersonic research is a good opportunity for collaboration, international collaboration. This is not over at all, because in the next H2020 program there is a call for collaboration, and so it's already open to Russia, Japan, and the US, and probably more partners. So what I want to underline is that we are focused on providing high-quality data to the regulation agencies such as ICAO, who are not taking sides here, advocating for or against civil supersonic. And I want to also mention that within the IFAR there is an existing noise working group led by ONERA, and that will be extended soon to noise concerns by supersonic transport, and also urban air mobility vehicles, which is quite a subject. Let me give the stage back to Michel Peters. Thank you for attention.
Okay, ladies and gentlemen, thank you very much. I think the presenters gave an excellent overview of the current research, what the various research organizations are doing, currently are conducting with respect to supersonic flight and sustainability aspects related to that. Now we are nice on time, so there is some room for Q&A. But I'm not very confident that I can answer all the questions, so I really would like to invite my colleagues to the stage, and then we are more than happy to receive and hopefully also answer all the questions. So I think the stage is open, so I see a hand over there. Yes, please. And guys, help me out.
Thank you all speakers for the interesting presentation relating to collaboration, and first of all in supersonic area. Two small questions maybe. All professors, all speakers relating to the, firstly, as I understand from Sergey presentation, ICAO are ready to have standard in 2025-26. And what is expectation of the manufacturers to enter in the service of the aircraft? What is your opinion relating when really will be expected to enter the service of the supersonic aircraft? And second question relating variable cycle engine, which is you mentioned in your presentation. After the first answer, I understand variable cycle engine also expected to be entering in the service also close to the 2025. Thank you for the answer.
Thank you. Our colleague from SIAM. Yes, I mean, I showed the whole entire roadmap of ICAO, and right by 2025, there is some expectation of approved regulations, rules, norms. Without that, we cannot talk about supersonic transport, or cannot do really supersonic transport. Our national expectation, from the status where we are today, I mentioned even in my presentation, like late 20s, I would say more cautious by 2030. I think we would be ready, to have, let's say, first flight or rollout or something like this, not earlier. Regarding various cycle engine, that's one of the most critical after low sonic boom and high efficiency aerodynamics. That's something we expect from you and from engine companies, so again, work together for pre-competitive research, but those kind of engines must be such efficient as their equivalent for subsonic aircraft. And you know that every percent of efficiency is kind of like almost like a revolution in engine world. So we still have to cover a very difficult road, you know, and, to develop such a kind of engine. But I know that you do some, I mean, we do in Russia some, we have some current efforts in this direction, and numerous experimental research already. But that's again, the progress must be achieved as minimum as no later than 25, 26. Otherwise, I mean, what kind of aircraft we design for what kind of engine. So engine is something starting point. Thank you.
Okay, I see a question over there. Yes, please.
Yuri Kuzmin, Russia. The question to all panelists, thank you. A lot of job was done, but all panelists talked about sonic boom and aerodynamic weight. But the economical quality of this project will depend on lifetime of the aircraft, in flight cycles and in time of landing. And there will be huge fatigue problem connected with a huge heat and huge pressure change during fast and high altitude level. And we have a lot of such problem in combat aircraft. For example, European Tornado are out of service not because they are bad or old, but because of resource. The question is, do IFAR plans intensive fatigue researches for supersonic flight, or it's just left for the far future? Thank you.
So it's a very interesting question. It's almost human psychology and how you're going to start gathering data for this. The design of the experiment is very, very important. How you gather the data, how you analyze these data. So I mentioned that what we're trying to do at NASA is to design an experiment that will subject various communities that are quite diverse to what it would be like if they were under the flight path of a commercial vehicle that would be flying regularly scheduled service. So we're looking at multiple overflights per day, 6 to 8, and gathering data for about 30 days. So then you have a question when you're doing flight research like this, something always breaks. So how long can you have a break in gathering your data for the data still to be valid? So there's an art and a science to this, and how the communities are going to respond. We have a lot of information about things like atmospheric conditions, humidity, because we've flown F-18s and flown them in a way to subject actual communities to 65 decibels of overpressure, and we understand some of that. So it is a very, very difficult psychological part of this too, and then how politics are going to play into it as far as when we have these data, what the actual recommendations or rule changes will be, and then when somebody actually enters a vehicle into service, which we think, as Sergey was talking about, sometime in the mid-2030s, if that could happen, and then really what kind of a response are you really going to get from the various communities that are being flown over. So I think that at least starts to address some of the questions that you posed.
I have a question about the environment. There was a lot of talk about the sonic boom, and rightfully so. But working on the HSCT about 20 plus years ago, at the end of it, we thought we could handle the NOx, but we're not sure if we can handle the H2O emissions at high altitudes. I don't keep up with this anymore, so I was wondering what is the state of the art and what's the consideration there?
So I can keep the record straight. Every time that I talk about this, I get this question. So we talk about sonic boom, but then we hear about high altitude emissions and landing and takeoff noise. So NASA has been doing research in all of these areas for 3 decades for supersonic flight. We think that we're making adequate progress along with the progress that we're making relative to sonic boom. The demonstrator that we're developing is just to demonstrate sonic boom. But we've been working both from a subsonic flight perspective with engine companies relative to landing and takeoff noise and emissions through our ERA project that we very successfully met some of the N+2 and got real close to the N+3 goals. While those aren't at the altitudes that we'll be flying, not exactly the same conditions, we think we have learned a lot and we've developed methodologies, simulation techniques, computational techniques to help us understand what those challenges are and how to address those. So we think that we're in lockstep with the sonic boom community relative to the other environmental effects. So we don't think that we're going to be out of phase relative to those. But it's a great question, and every time I talk about this, I get that question.
Sorry, I have a question here. And actually the question is also for Ed, for NASA. Because NASA has done a lot of research in this area in supersonic and even hypersonic. And some of the work from the 70s, 80s has a model which you wouldn't have the boom problem taking off or landing. And that's the oblique wing project. And actually, since NASA had that project, and it was an X-plane fluke, afterwards, DARPA also had a program continuing that. And I'm just wondering, what's the status of that? I mean, in fact, if you use that model, you wouldn't have to worry about all this boom problem. So, can you comment on that?
So you've got technology and you've got the reality of certifying a vehicle. Certifying a commercial vehicle with an oblique wing, I think, would be very, very difficult. And so this is, when any of the configurations that we talk about, I mean, we had a plenary session earlier where we were talking about blended wing bodies. We were talking about the DA configuration that Aurora has built, the truss brace wing. Any of these is a challenge within itself. It's a challenge domestically, it's a challenge internationally of how you certify those kind of aircraft. So, Susan, I think that the oblique wing has great potential, but we're working in the reality of, as Sergey talked about, something that might could be flying in 2030. And just from a personal point of view, not a NASA point of view, while the technology may be there for an oblique wing, I don't think that we could get a vehicle certified that would enter in service in those times. That's a huge challenge when you've got such a change in a revolutionary change in what the configuration is.
Other questions? One in the back.
Thank you. One question about I understand the value of speed, but do you see a risk that you could trigger a wider discussion about how much of the resources can be allocated to a small, wealthy group of people? I would love to hear also the NASA view on that, to the situation of the current administration, but maybe it's also good to have an outside view on that. Professor Henke, do you have an opinion on that one?
Of course, I have an opinion, but that may be another story. I think we really have to distinguish between the different points. One is technology, and we're just talking technologies, and it just came to my mind. If you look at the stage here, we are all researchers, and we solve technology problems on CO2, on NOx, on booms, on fatigue, and all that sort of things. That's a prerequisite. We need that. The next would be certification rules, and we already touched that. We had the Berlin Aviation Summit in May this year, and then a presentation of authorities saying it may last some 5 to 10 years until the certification rule becomes active. So assuming 2030 could be a good idea if we start now. It may last 5 to 10 years until we have certification rules. But finally, we need a pressure to do something like a supersonic aircraft. That's what I briefly addressed. And I'm still wondering if we have a Mach 1.4 aircraft and compare it to a regional jet or a small business jet that flies at Mach 0.9. And on a 6-hour mission, about 1 to 2 hours is all the landing and takeoff cycle. So we have to save money between the time between the 4 remaining hours in cruise. And the difference in speed is not that much. So you may gain some 20–30% in time. And it's really industrially worth, to put in some 10, 20, 30 billion euro for this state of. This we don't know. We are researchers, we can give the prerequisite, the solutions, and the market will answer this. If this other question, for how many people will that be available or not, that's really a social, ethical questions which have also be addressed, but not that much by people who work on sonic boom problems. So I agree, it is a question, it's a societal question, but that's not us to answer it. But the first 3 prerequisite technologies, certification, and finally industrial pressure, really to do it, that be the major ones. And 2030 may be maybe even an early date. Thanks.
Other questions? One in the back, yes.
One of the main lessons learned after the HISAC project was that the boom intensity strongly depends on the mass of the aircraft. Therefore, during the HISAC project, the maximum takeoff weight was limited to about 24 tons. And what means that the number of passengers was reduced to 10 and plus 2 pilots, so maximum 12 altogether. Based on the recent research, can we hope that the years to come, it will be possible to build a supersonic aircraft which could fly over the land, taking more passengers, I mean 60, 70, 80? That's my question. Thank you.
So the evidence that we have seen at NASA says yes, that you will be able to do that. So you've got a lot of things working for you. You're going to be flying at very high altitude, so altitude attenuates the overpressure. The new design requirements that have been developed at NASA and other research organizations around the world show that there's a way to change that end wave to something that's not a boom, but as one of my dear colleagues at Boeing used to call it, no different than thunder on a summer night. If you're listening for it, you may hear it, but if you're not listening for it, it just could be lost in the background. So we believe it's there. There are certainly other companies that think that you're going to be able to do this, and they're already moving out on designs. So the proof is going to be as we actually build the aircraft, fly them, and gather the data. And then what the marketplace will bear relative to the economies associated with such a vehicle.
Okay, great. Ladies and gentlemen, thanks for the questions. I want to really keep up with time and to have ample time available for, I would say, the main part of this lecture series, and that is, of course, the award ceremony for the ICAS IFAR award. Now let's see, we prepared a couple of slides. So some information about our common award. It's a global award to honor an individual who has made a significant contribution to aeronautical science within his or her doctoral thesis.
And the eligibility says that it has to be within 2 years of the date after the PhD was obtained, and it has to be under 40 years old at the nominating date. So the award, the award winner is selected by the IFAR evaluation team and the ICAS Honors and Awards Committee. Out of the candidates nominated by the IFAR member organizations worldwide, the 26 organizations. And it was launched in 2016. I think Professor Joe Zodarov was the one who first proposed that.
Okay, and now of course the main dish. So the award, the second ICAS IFAR award is awarded to Dr. and hopefully I pronounce your name correctly, Rei Yamashita from the University of Cambridge, sponsored by the Japan Society for Promotion of Science Overseas, and he is a research fellow on that. And if I read the recipient, the citation, it says that in recognition of his exceptional research and significant contribution to aeronautical sciences through the PhD thesis, full field simulation for sonic boom propagation through real atmosphere. Dr. Yamashita, can I invite you to the stage? So first, so perhaps you can stand there. Well, perhaps you can go in the background. Not over yet. Oh, yeah.
Thank you very much. I'd like to extend my warmest greetings to ICAS, IFAR, and JAXA who nominated me for this award. I am very delighted to be selected as a winner of ICAS IFAR award. Winning this prestigious award is something that I never could have imagined. I'd like to express my deepest appreciation to Professor Kojiro Suzuki at the University of Tokyo, who gave me a chance to conduct very challenging research during my PhD thesis. And also, I'd like to give my special thanks to all members of the Suzuki Laboratory and my family for their support. I hope I can continue making further contribution to aeronautical science. Thank you.
So great. Axel Probst asked me to give some logistics.